Let's get started. Welcome to my talk. I'm Taesoo Kim, an associate professor at Georgia Tech, and I'm also working as a VP at Samsung Research. Today, I'm going to talk about our journey to fight against memory safety bug. In our group at Georgia Tech, we have discussed a lot about what exactly is memory safety bug, and what type of research we should do, or whether we should continue work on this area or not. This talk is really summary of what we discussed with my student and our opinion on how to really improve the current status of core. I hope that at the end of this talk, you got all excited about memory safety related research again and join our efforts in making secure world. Since the creation of modern computer systems, memory safety issues have been a long-standing problem. But still today, it is considered the most severe and dominant type of security issues. This figure shows the percentage of various types of security bugs in Microsoft product over the year. For example, this region marked red shows how many times the user after free bugs are exploited in the wild, which has become one of the most dominant type of bugs found in Microsoft software. What's interesting to me is that if we combine all the memory safety bugs together, they constantly represent about 70% of the entire security bugs. Such a number is consistently reported across other types of popular software like Chrome web browsers and Android from Google. In other words, according to what we have been discussing so far, the memory safety sounds like a very appealing area and also very important area of research. When I first started preparing for this talk, I thought the talk is supposed to be about the success story of my research. Like, we have published more than 100 papers in top security conferences, each of which describe amazing new technique that can prevent a particular class of vulnerability. I wanted to claim as a result of my research, the memory safety issues that we have been working very hard on are really resolved, or now we can truly understand the nature of the memory safety bug. So we all have to move on to the other area as a result. Unfortunately, though, today's security landscape is not quite different from where I started several years ago. In fact, the number of vulnerability increased quite significantly, unlike what we wish. If you see the graph carefully enough, the number of bugs in each type constantly increase over the year, yet the percentages seem staying the same. But don't be discouraged yet. We gonna share our opinion about how to improve the current situation drastically better later in my talk. So what about 10 years from now? I believe the current trend will stand the same, meaning that we will see the increasing number of memory safety bugs in the future because the amount of code is keep increasing fastly over time, and many of them will be written by non-security experts more and more. But thanks to our community efforts in defensive measures like mitigations and isolations and sandboxing, I believe exploitation of such bugs itself become much difficult. And perhaps many of the state-of-the-art defensive mechanisms become practical and deployable thanks to advances in hardware features, for example. I also believe that the similar type of memory safety issues will repeatedly appear in many of the emerging computing environments, like Internet of Things and trust execution environment, or even confidential computing, because the memory safety issues are tightly related to the modern computer architectures and programming language. In this talk, I like to claim that the memory safety is rather a fundamental concern of memory abstractions, and it will happen as long as we have a discrepancy between what we assume in the source code and what exactly executed on the machine. If you're a new PhD student seeking new research area, do not just hesitate in jumping this exciting area simply because it's a long-standing problem and technically difficult to catch up. There'll be tons of opportunity in this field even in the future. This is an outline of my talk. First, we're going to revisit the definition of memory safety, and then we're going to define the concept of safe APIs under the context of memory safety. And I will conclude my talk by introducing new language called Rust and its approaches to memory safety. Rust's approach is so amazing that I really encourage all of them for immediate adoption. but there are a lot of ideas and principles that we can learn from it, even when we're developing new software with other languages like C or C++. One key message of this talk is that as an advocate of Rust, I truly believe adopting Rust is the most promising way to change the current security landscape, and I will describe their approaches in details in my talk. We often hear that the best way to avoid memory safety issues is simply not using low-level programming languages like C or C++, and simply adopt high-level programming languages like Java or Python. It is not completely untrue statement, but why we are thinking like that? The C programming language provides a very minimal abstraction of physical RAM, what we call memory, although the memory abstraction is so primitive, and one can even compare it with the tape of tuning machine. It is a very universal and portable representation of virtually all of the existing computer architecture today. It is really the ideal and standard way to abstract the physical RAM. More specifically, the memory in C provides sequential storage space that can be accessed in byte-addressable manner. Simply put, given an address, it will return corresponding data as a sequence of bit. If you can put anything that can be encoded as a bit into the storage, including the address in C as well. In other words, there's no type or any high-level construction associated with the storage, and it's really up to the language in how to interpret the data itself. However, in most high-level languages, there exists an intermediate layer between the language and memory known as language runtime. The language runtime, also known as the managed runtime, virtual machines, or very thin layer of garbage collector, prevent direct access to the memory from the program, but provide a storage abstraction based on object, which can only be accessed through their name, such as a symbol. Although the language runtime still interact with the underlying hardware, like how C does, the notion of addresses are not typically exposed to the language layer. In other words, it seems like we call the high-level programming languages memory safe simply because they don't have a notion of memory like C at the first place. To provide the memory safety in high-level language, the language designer intentionally encapsulate the notion of the memory in C from the language itself. Let's just think about the problem a little differently. You might see the JS Linux project that emulate the Linux operating system program running on the browser. But not limited to the Linux, the underlying emulator called TinyEMU perform all sorts of emulations, like full system emulations of x86 binary, for instance. So we can even run a full Linux and Windows operating system, as well as a full-fledged web browsers inside. In this setting, we are running a program written in a memory unsafe language like C on an emulator written in a high-level languages, in this case JavaScript. In other words, all the program written with a memory unsafe language can now run together with the emulator within the memory safe high-level programming language. Since the emulator is one executing the instruction from the unsafe program and is free from memory safety issues, the execution of the program is indeed free from memory unsafe bug. More interestingly, TinyEMU is originally written in C and transcompiled to the JavaScript by using emscripten. It means that any C program can be memory safe by simply transcompiling them to the JavaScript. So did I just find a universal way to eliminate all memory safety issues in C program? Perhaps not, because the existing memory unsafe bug of each C program are still exploitable by an attacker. If there exists a bug inside the original C code, and everything is precisely emulated by the memory safe emulator itself, then the exploit will be emulated as if it worked on the real x86 hardware. Although the emulator is memory safe and interprets its instruction one by one in the safe manner, it behaves as if it's being exploited, or its control flow is hijacked by the attacker. In other words, memory safety is not a holistic or universal concern, but rather a localized concern of each program or layer. And what matters is whether memory abstraction that each program is built on is bypassable or not by an attacker. When it comes to the emulation metaphor, the memory that emulator care about is indeed different from the memory the program is built on. So the memory safety box of the program is not the memory safety issue of the emulator. Larger people in the community recklessly categorize the just-in-time bugs in the browser as a memory safety issues and blame the use of unsafe language in the development. In fact, the JIT bug are mostly logical issues and won't go away even if we are using high-level languages like Java. Again, when we say memory safety issue in JIT, it means the memory abstraction of the JIT instructions, not the memory of the host program. And it is not even relevant to the choice of the language of the host program. So in other words, it is really important to clarify the context and layer when it comes to memory safety. So far, we have discussed the meaning of the memory safety for low-level, high-level programming language perspective, and also claim that the memory safety is a localized concern of individual programmer layer that is built on its own model of memory. So let's think about this idea a little bit more concretely by using a typical example of memory unsafe bug in C. So we commonly categorize a memory unsafe bugs into two: the spatial violation, which is related to the space, and temporal violation, which is an error associated with timing. This is the simplest form of the spatial vulnerability called a buffer overflow. If there exists an overflow in a stack, we call stack overflow. If it happens on a heap, we call heap overflow. Both types of overflow bugs allow an attacker to override beyond the legitimately allocated memory of the buffer. For example, in this code, we allocated an array of 3 elements in a stack, but access fourth element in the array, which is beyond the allocated memory of the array. So why matter? Because of this vulnerability, an attacker can override important data allocated right next to it. For example, control dependent data like return address or function pointer or heap metadata can be overwritten and lead to an arbitrary execution as a result. In comparison, what about we make a similar mistake in high-level languages like Python? If an attacker accesses beyond the allocated buffer, like accessing additional slot that is beyond the length of list in Python, the language runtime stop the execution and simply prevent it from exploitation, unlike C. Again, under such a condition, the language managed to stop instead of leaving unknown state nor being exploited. Why that's the case in Python? Unlike the access to the array in C is simply translated into the pointer calculation access, the access to the list in Python is a function invocation. It's like set item with an index and corresponding data. And the language runtime interpose and compare its index with the length. If the length and index do not match, the runtime simply terminates the program. Admittedly, such an interposition is exactly what she wished to avoid at the first place, but many of high-level programming languages intentionally do to make the program free from memory safety issues. Another type of vulnerability is called temporal safety violations, also simply known as dangling pointer. For example, in order to allocate heap memory in C, we need to invoke malloc along with the necessary size as an argument. So whenever the memory is needed, it's a developer's responsibility to deallocate the memory by invoking a free function. However, once the memory is free, the memory should not be accessed via dangling pointer and lead to a potential exploitation. The implication of such bugs is more subtle than what you think. As shown in the slide, accessing the free region immediately after means that likely you're going to access the same data as expected. However, in a real user of the free bug, the time window between free and incorrect access is very long. And during the window, attacker can place important data like function pointer in the right place that the dangling pointer pointing to. An attacker can override them with an arbitrary data of their own choice. In Python, in many cases, a developer doesn't have to worry at all about the deallocation of an object, thanks to its garbage collector based on reference counting. If a developer wants, one can opt in for an unexplicit control, like deleting a large object like list with the delete operator. Once an object is deleted, the language runtime doesn't allow further access to an object anymore. If it happens, the execution will be stopped, unlike being abused or for potential exploitation in C. When a symbol, the name of object, is inquired by the runtime, then it look up the corresponding object and allow further access to the object through the interface. If this is a stark contrast to the C, that once a pointer is obtained, we can access the underlying data without any further validation. So far, in terms of temporal and spatial memory safety, it seems like a high-level programming language does a pretty good job of stopping them from exploitation. So here comes a catch. When it comes to memory safety, along with the buffer overflow and dangling pointer as example of spatial and temporal violation, researchers often consider format string vulnerability as a memory safety violation as well. Note that not limited to this remarkable blog posting, it is very common practice to categorize memory safety into two classes. This is how we do formatting in C. We provide a format specifier like %f for formatting string and %p for a pointer as an argument to the printf functions in C. When printf is executing at runtime, it interprets the format specifier and performs formatting of the provided argument one by one. For some reasons, if an attacker can influence the content of the format specifier, it can lead to an arbitrary read or arbitrary write. And they can be relatively easily chained for an arbitrary execution schedule. In fact, there are lots of context needed to actually exploit this bug, like location of the format specifier and possibility of abusing frame pointer and the existence of various mitigation schedules. All of them are pretty interesting subject of their own as exploitation technique. If you're interested in knowing the details of such exploitation technique, please check out labs and tutorials in the binary exploitation class that we designed and have been offering at Georgia Tech. You will be able to learn these practical skill sets as part of this semester-wide CTF-like competition. Of course, we made all the materials and video publicly available for use. The implication of the format string vulnerability is much more subtle than you might think. The researchers in our community have studied and proved the tuning completeness of this format string vulnerability with a technique known as printf-oriented programming. Simply put, given a single exploit payload to the format specifier buffer, one can perform an arbitrary computation, which is equivalent to the arbitrary computations of tuning machine. Many of the interesting payloads are demonstrated, like tic-tac-toe or brain fog interpreter, for instance. Even more, DARPA Amy project led by Sergey has been sponsoring multi-million-dollar funding to truly understand the nature of such vulnerability with an abstraction known as a VR machine. In fact, this is a pretty novel idea to observe certain behavior of the code with a lens of computational machine. The participants of the DARPA Amy project, including ourselves, proposed lots of autonomous technique to reason about the existence of such a property, given arbitrary implementation of printf-like function. Without telling the use of format specifier or their model or specification, our analysis technique can recognize some primitive required for VR machine and formulate the exploit by chaining them. So, the format string vulnerability sounds like an interesting class of bug. But is it really temporal violations or spatial one? Does the language say anything about such a usage? It simply passed the legitimate buffer to the printf function. Why do people think it causes undefined behavior and memory safety issue? In fact, it is not related to the language specification, but is a memory unsafe bug because the API designer says so. The bug section of the printf man page kindly describes the potential misuse and its security implication of potential overriding due to the percentage n from the untrusted user. These are the preconditions of exhibiting the correct behavior of the printf, but again, it doesn't seem like relevant to either temporal or spatial violation. What about Python? It has much modern template-based formatting scheme like string format. It has pretty similar format specifier rules like C, but we can perform formatting in more structural manner. So what about we provide an attacker control format specifier to the format function? Similar to temporal and spatial violation, you might expect that it might stop the execution from exploitation. In fact, by providing a payload like the one shown in the slide, an attacker can launch arbitrarily the read against the program even in Python. More specifically, an attacker can provide a format specifier that chases the property chain of the Python object all the way up to the global dictionary and access the arbitrary variable of their own. This can be particularly problematic if an attacker can read a secret key in a web framework like Flask, which is used to encrypt the contents of the cookie, for instance. Then, what's the root cause of this vulnerability in both languages? The printf functions in C interpret the attacker-provided format specifier and either generate the pointer out of the air or change their usage, like changing the read or read to the right of the pointer. It is subtly related to the way the C language implements support periodic functions as well. By changing the format specifier, the printf will treat the way to interpret values in the stack or register in arbitrary manner. Similarly, in Python, the format functions interpret the format specifiers and generate the symbols of an object from the provided string. It means that an attacker can modify the string and influence the way to convert the string to a symbol of an object in an arbitrary manner. According to the discussion so far, do you still think that these two vulnerabilities are essentially different in their nature? If the format string vulnerability is indeed a memory safety issue in C, then can we say this is also memory unsafe bug in Python? Considering that Python abstracts the memory as an object-based storage, the vulnerability in Python allows an attacker to influence which object to be read, unlike what the developer originally intended. Isn't it essentially the same symptoms in terms of bypassing the storage abstractions in both languages, namely the memory in C and the object abstractions in Python? In this talk, I like to argue both are the same in nature. And the better way to describe the memory safety issue is as a symptom of an arbitrarily or unmanaged generations and uses of index to storage abstraction that each language is built on. For example, the some code snippet in the printf incorrectly generate a pointer given an attacker's input, and Python also generates a symbol from an attacker-provided string, both cause memory safety issue. If we far-fetch this idea further, many of the vulnerabilities that we are studying in the context of C show remarkable similarity as Python. For example, code reuse, code injections, or control flow hijacking bugs are similar in nature in Python's import, eval, or custom serialization or parsing related vulnerability. Of course, we don't naively say they are all memory unsafe bugs in Python because they doesn't have any. But in terms of object storage, I can see these are definitely in a similar class, having compatible property in C. This is a relatively controversial idea because many developers feel like Python is more secure than C. But I think it's simply because many of these vulnerabilities happen implicitly in C, but happen in explicit places in Python. So we're going to discuss about this later in my talk as well. There have been a lot of attempts to understand memory safety in the past. The simplest way is to consider all the memory safety bugs as a result of undefined behavior. But unfortunately, this idea is rather too broad to highlight the characteristics of memory safety bug. For example, an overflow in sign arithmetic is undefined behavior, yet mostly benign in terms of exploitation. Another interesting idea is to consider memory unsafety as a feasibility to access undefined region of the memory, such as a return address on the stack or heaps metadata. Unfortunately, it is not precise enough to include the internal overflow of the data structure. For example, as shown in the slide, an overflow of the buffer in the struct can overflow to the size parameter of the same struct, not limited to the undefined region of the memory. The more accurate way is to treat pointer as a capability to access memory. In this model, each pointer has an associated region of the memory, and whenever the pointer are used differently than their capability, we consider the memory unsafe bugs are triggered. This is a pretty accurate description of the symptom of memory unsafety issues, but it doesn't clearly appeal to me how to think of the format string vulnerability in this frame of thought. Even more, how to fix them. So I propose a more actionable definition of the memory safety. Specifically, I like to embrace more actionable guideline in the definition, which I believe is very useful in building the foundation of memory safe program. We define that memory unsafe bug are caused by the unmanaged generation or uses of an index to the language storage abstraction. It is actionable because to fix the memory unsafe bug, one should resolve the issue of incorrect generation or uses of a pointer in C, for instance. In this definition, we use the term manage when the compiler or language runtime enforces on rules in generations or uses of indexes. In fact, it's more inclusive definitions than capability-based definition, because not all of the unmanaged generations or uses would trigger the memory safety issue. I also emphasize the correct generation of index more than its uses because it's a more desirable way to fix the vulnerability, which we're going to discuss in detail later in my talk. It is also extensible to other languages that might have different or sometimes more than one definition of index to the storage abstraction. So let me discuss this idea with a concrete context. This is a format string vulnerability in sudo that allow a local privilege escalation attack. This sudo debug function shown in the slide is a custom printf-like function, and accept the format specifier as argument. It first create a new format specifier by concatenating the program name with the provided format specifier, and then pass the new buffer to the vprintf function. The developer didn't realize the attacker can manipulate the format specifier by changing the process name. For example, like simply creating a symbolic link to the sudo binary, for example. Given a proper attack payload, an attacker can gain a root privilege of the system. How to fix this vulnerability? Instead of prepending the program name to the buffer for format specifier, we can simply print out the name together with the interpreted output. As shown in the slide, it is commonly regarded as a mistake by the use of printf. And so, it is also the user's responsibility to fix the code to resolve this memory safety issue. Let's think about the approaches to mitigate the format string vulnerability. There are roughly three common approaches. First, as it is uncommon to use %n, one can restrict that %n is only available when the format specifier is constructed in read-only memory region. Second, once we found out on esoteric uses of $, the positional argument of the specifier in common exploit, we can impose additional rules like all the positional arguments should be used as a whole. Otherwise, the format specifier won't be interpreted. Lastly, we can embrace high-level semantics like printf compatible format specifier that the compiler can provide the basic sanity check on the given format specifier at compilation time. Unfortunately, these approaches of limiting the usage of the printf are mostly afterthought and largely heuristic against the exploit, so that they always leave some loopholes in their mitigation. If you consider the amount of uses of printf and custom printf-like functions everywhere in the code base, it makes it extremely challenging to sanitize all these use cases in a holistic manner. In fact, this really illustrates our software development practice nowadays. We never thought of challenging the correctness of printf, but instead attempted to resolve the issue by patching the usage of the printf. A better approach, however, is to design printf such a way that any invocation of the printf free from memory safety issues at the first place. According to our definition of the memory safety, printf is the one that generate and use of arbitrary pointer, so it should be fixed. Admittedly though, it's very challenging to design such an API, given the lack of proper support by the C language. And here comes Rust. In terms of memory safety, there is no unsafe invocation to any Rust functions. If such a problem ever happens, it's a problem of API designer, not users. This is also nicely aligned with our definition of memory safety, since printf can generate an arbitrary pointer from a user's input. Again, it's desirable for printf to address this problem, so that we can make any invocation of the printf free from memory safety issue. Not only that, an invocation of printf or format in Rust is interpreted by the compiler, meaning that the correctness of formatting rules are checked and expanded at compilation time. For example, as shown in the slide, Rust can recognize the type and format specifier rule via its rich macro subsystem and determine the formatting rules at compilation time. As we don't need to parse the format specifier at runtime, we can do performant yet secure formatting in Rust. Rust can also prevent spatial and temporal violation thanks to its expressive type systems and lifetime check. Both are very important building blocks for memory safety, but today I'd like to focus more on explaining Rust's unique feature, the ownership, and lifetime in the perspective of memory safety. To understand the concept of lifetime in Rust, let me first explain the concept of ownership and borrowing. In Rust, we say a variable owns a value. In this example, a variable x and y own the value hello and world respectively. When we assign a variable, the ownership changes accordingly. For example, when we assign y to x, the ownership of the value world moves to the variable x. The idea of ownership is tightly related to the concept of memory management. In this example, when we assign hello and world to x and y, the memory allocations happen accordingly. When the ownership transfer, deallocations happen as well. Since the variable x doesn't own the value hello anymore, the compiler inserts the deallocation procedure of the string hello. Also, when the variable goes out of scope, the value that variable own will be deallocated as the variable is not accessible anymore. Again, following the notion of the ownership, the compiler automatically inserts this allocation and deallocation routine for the programmer. The ownership-based approach is great for resource management, but results in very suboptimal code for memory allocations and deallocation. Not only that, it's very inconvenient to use. In this example, once the x value moves to y, any access through x results in a compilation error. To be practical, Rust provides the concept of borrowing, also known as references. Simply put, a variable can borrow the value from its own variable by simply attaching the ampersand sign in the assignment. With a reference similar to the capabilities-based system, one can always access the value it points to. In Rust, we have two different ways of borrowing. One can borrow a value for reading, known as a shared reference, or for writing, known as mutable reference. For reading, developer can create as many shared references as possible so that we can concurrently access the value with different references. In this example shown in the slide, the shared reference to x is assigned to y, and z, and all of the variables can read the value hello as a result. For writing, however, there should be only one mutable reference. In other words, any attempt to create multiple mutable references cause a compilation error. Finally, here comes the Rust safety rule. In Rust, we can create either many shared references or only one mutable reference, but not both of them at the same time. Such an invariant which is assured by compiler is one of the important foundations in building safe APIs. Let me give you some examples. A stale iterator is one of the error-prone design patterns in C++. If a container is modified while iterating element of container, the iterator becomes stale, meaning that it might point to the memory the container doesn't own anymore. For example, if we insert or delete an element of the vectors in C++, all of the outstanding iterator are potentially stale, and any excess will cause a memory safety issue. However, in Rust, any such an attempt causes a compilation error, because when we attempted to modify the vector, there exists an outstanding shared reference, the iterator. Aliasing is another great example. In C, given two pointer, the compiler can assume both are distinct, making hard to apply performance optimization technique. For example, if we provide two overlapping pointer to the main copy, it causes memory safety issue. So commonly consider that it's a user's responsibility to follow mem copies safety guideline. In Rust, however, a mutable reference and shared reference can exist at the same time. For example, if the clone from slice function, two references never point to the same value thanks to its safety rule. In short, these rules make Rust generate safer and better optimized code as a result. These are the really tip of the iceberg. Rust provides lots of interesting building block and well-thought idiom to write better and safer API. If you're interested in, please check our course on designing operating system. You can learn how to build toy operating system for Raspberry Pi by using Rust from scratch. In summary, Rust has a clean model of memory safety based on its ownership and borrowing and their safety rules. Also, in terms of our definition of memory safety, since references can be generated and used in the controlled manner, the following the compiler's rule. It is simply free from memory safety issue. However, it sounds like too good to be true. Is it really expressive enough to build system software, like doing memory mapped I/O or accessing hardware or even invoking a system call? To solve this issue, Rust provides a notion of unsafe in the program, which enable all these explicitly in a controlled manner. In safe Rust, the compiler by default can automatically guarantee the memory safety following the safety rule that we discussed so far. However, in unsafe Rust, it's a developer's responsibility to guarantee the correctness of memory safety issue. What makes it unique about Rust is the language draw a clear line between safe and unsafe words. In the safe word, a reference exists only as an index to the storage, and the compiler guarantees its safety by managing its generations and uses at compilation time. In the unsafe word, there exists a concept of row pointer, which developers should manage its use for memory safety. Interestingly, in Rust, it is considered safe to generate the row pointer either by casting from a reference or through pointer arithmetic because it's considered memory safe as far as it is not used. By using unsafe Rust, we can also generate reference, but again, its safety should be assured by the developer. There are two ways to use unsafe Rust. First, one can declare a function is unsafe. In this case, users are responsible for memory safety, similar to printf in C. But still, users can only use the unsafe functions in the unsafe context. Second, if a developer determines that the use of unsafe is secure, like checking the length of an element before invoking an unsafe function, the API can be declared safe, meaning that it can be invoked in any context. A recommended practice of Rust, of course, is to minimize the use of unsafe. According to our experiences, most user space applications can be easily built without using any unsafe context in their code. Thanks to such a clear separation of safe and unsafe, the reasoning of memory safety in Rust is much more localized than any other programming languages. To assure memory safety in Rust, developers should audit unsafe and related code of their own to assure memory safety. This is a stark contrast to the CCS approach where we had to find and check insecure uses of printf, as printf is not designed to handle all the possible domain of the input. Unlike C, by using Rust, we can keep building our software on the solid and memory safe foundation. You might worry about unsafe usage in Rust, and I like to emphasize that such an explicit separation of safe and unsafe code in Rust really help a lot in finding memory unsafe bug in the code as well. For example, the Rudra, we recently published in SOSP, can recognize error-prone pattern in the unsafe code in the entire package registry. The analysis can be localized thanks to its explicit safety control, so very scalable. About 40,000 packages could be checked in a few hours. With our tool, we found over 200 memory unsafe bugs in the Rust packages, which represent about 50% of such bugs in the entire history of the Rust. In Rudra, we devised algorithm to find three unique bug patterns in unsafe code in Rust, namely panic safety and high order invariant and send and sync variance. If you'd like to know details of each type, please check our paper and code in the repository, along with a lot of POC exploit we wrote as a demonstration. But I'd like to emphasize the important aspect of Rust that really enabled this research. First, explicit separation of safe and unsafe code allow us to focus on analyzing code that really matter. Second, the clear definition of memory safety allow us to find bugs in generic type and trait of the library even before they are materialized or used by other programs. I'm currently in my sabbatical year and having a role as a VP at Samsung Research. And together with a group of researchers and engineers at Samsung, we are currently designing a Rust-based operating system for secure element in our SoC. Although memory safety is our utmost important goal of the project, we need to make lots of security decisions, like avoiding panics for availability and minimizing usage of unsafe and building safe abstraction for underlying hardware. I'd like to emphasize that Rust is really expressive enough to encapsulate all of our requirements with minimal performance overhead. Not limited to memory safety, using Rust for the implementation also help a lot in applying formal method and verification approach to our project as well. If you're interested in knowing more about Samsung Research and this project, then feel free to approach us in the sponsor's virtual booth. These are the important messages in my talk. When I talking to security researchers and also my PhD student, I got the impression that they're really into the research of memory safety and exploitation technique. But they got a little bit discouraged because it's a long-standing problem that community is already aware of. And it's technically very challenging to accomplish anything within short period of their career. But I wanted to encourage that the memory safety is really a fundamental concern, so you don't have to worry about future career. And it's a really exciting research subject that deserve much more attention from the community. In next 10 years, I believe we're still going to talk about the memory safety, but in various other contexts like new programming languages, emerging computing involvement, let alone the legacy and gigantic code bases that we have, operating system kernel, and web browser. Second, I hope you got interested in Rust and its way of building memory safe program if you haven't tried it seriously. Okay, forget about everything I just said. Take this one message. Please use Rust. From the lessons learned from my own career, Rust is the most practical and promising way to make memory safe work in next 10 years. Thank you for listening to my talk. If you're interested in talking to me about Georgia Tech or Samsung, feel free to reach out to me through various channels on the internet. Thank you.